All right. Good afternoon, everybody. Thank you so much for joining this CTL seminar, come webinar. We're extremely honored to have with us Professor Suresh Sethi with us today. In fact, his trip is long, long due. In fact, we were planning it for a couple of years and finally it materialized today. A bit about Professor Sethi. Yeah, he's a very well-known figure in the whole area of operations management. And currently, he serves as the Eugene McDermott Chair Professor of Operations Management and the Director of the Center for Intelligent Supply Networks at the UT Dallas. He has written 11 books and published over 400 research papers in manufacturing and operations management. He also works with the interface of finance, economics, marketing, and he's well known in optimization theory. In fact, I'm sure some of you have watched his recent articles by UT Dallas themselves. There was a lot of press releases about his 80th birthday and the contributions that he have done to UT Dallas. In fact, he's also said to be initiating the OM area at UT Dallas and creating that into a research powerhouse, what it stands for today. So I think he deserves a round of applause for doing that for the whole OM community. We are extremely fortunate because this also happens to be his last tour on his 80th birthday. He's just flying from here in few days to Hanoi, where
Calcutta, then Hanoi.
Calcutta and then Hanoi, and they're again celebrating his 80th birthday at Hanoi's conference. So he has given several keynote talks, and two conferences were organized in 2005 and again at UT Dallas in 2006 with the Nobel laureate in economics, Harry A. Markowitz, and he was a keynote speaker. In 2025, there will be three conferences and there were already two. This is the third one happening. The UT Dallas, there was one at the Magna Carta Island in London, and the third one is going to happen very shortly at the National Economics University in Hanoi. Two books have been edited in his honor. POMS awards the Suresh Sethi Best Interdisciplinary Paper Award every 2 years, and beginning in 2085. He has won several awards. Some of the notable ones are he's a fellow of the Canadian Academy of Science. He's an IEEE fellow, Informs fellow, SIAM fellow, POMS fellow, AAAS fellow. Is that a artificial
Association for Advancement in Science?
Okay. And he's also known as he's a Distinguished Alum Award from the IIT Bombay, from where he graduated in 1967. Is that correct? 1967. So he told me that he used to travel at least twice every year from Rajasthan to Bombay, and he used to go through the Ahmedabad station. This is the first time he visiting the city in 80 years. That deserves a round of applause, and we could make it happen, right?
Absolutely.
He also got the Carnegie Mellon University Tappert School of Business Alumni Achievement Award, and he also was the POMS president in 2012. This is, of course, a very short bio of him. The more you learn about him, it expands as an universe. So without much delay, I think I'll give the floor and the Zoom both to you. There are a lot of participants online as well, so we can get it started, Professor Sethi.
Okay. Well, thank you, Devjit, for introduction and your invitation here. I do like the fact that this is the first time I'm inside the city, and I decided that I will stay 1 or 2 extra days so that I get to know the city, and I think that I've done that well. Last 2 days I've been going around. So I've seen maybe more than some of the people who live here, because I went to Jama Masjid where your logo is, the Jali or whatever they call it. I'm quite interested in some of these things because architecture is one of my it's one of my interests as well. So it's a good idea to see that. And when I came to Hatti Singh Jain Temple, went to Sabarmati Ashram, went to Adala's Stepwell, went to Sun Temple in Modera, went to Rani Ki Amal also. So there were some nice places to visit. We still have a few more places. Sarkez Rosa is another one. And another one is Ahmedabad Gufa. I haven't seen those two yet. So maybe 3rd of December, I will do that. Okay. So Um, I will talk about this talk today. So let me give you some brief introduction about what is going on here. So it turned out that about 10 years ago or so, I realized that there's something called supply chain coordination in our field. I suppose you know all of that. It is something to do with different agents in supply chain coordinating under some contract so that the whole supply chain is maximized, not just the individual profits of the agents. And it turns out that the entire literature was just single period. One problem, finished. And I was wondering why no one ever figured out how to coordinate a supply chain if the supply chain takes more than one period. And I thought maybe it was just mathematically complicated. So people thought maybe it's not, we can be all charged, all the academics. We look at something that has a nice formulas, but anything becomes more complicated, we call it that is left for the future researcher. That is one of the line in the paper that everybody has, and that future research sometimes is not doable, but you write it anyway. So that's what I thought. Or I thought that maybe single period gives all the details. So you don't need the two periods, or you don't need multi-period. But that you can only do by solving a multi-period problem to see whether any new insights get learned from there. And that was never done. So I put that for myself that I should try to figure this problem. And I found out that the big problem was not mathematics. The big problem was supply chain coordination is modeled as what is called a leader-followership game. It's also called the Stackelberg game in our field. And Stackelberg wrote a book on game theory about this game, and that's a single period game. And no one in our field knew how to find an equilibrium in a Stackelberg game if the game is a dynamic game. There have been some papers in control theory literature and math literature that did it, but they got buried. One of the references a guy from Cyprus and Greece, and I know him. And when we looked at this paper, that paper is almost inscrutable. You can read the paper and not understand what's going on. It's just that they don't know how to write. So we had to spend time reading that, and then we understood what's going on, but we also found out that there were not everything that's there, and so we had to generalize that. I wrote a couple of papers in Time Journal of Control. And once you have the Stackelberg game, then you can model the two-period supply chain problem, and you can actually show that supply chain can be coordinated. So I'm going to basically give you the first thing I want you to learn from here, that there is a concept of equilibrium in a two-period supply chain or a multi-period supply chain. And the second one, that it can be used for coordinating the supply chain. I think the first may be more important because that has more application in other areas than just supply chain. So that's the first plot. And then another part, you see the mixed leadership game. And that game is another thing that in our literature, we have a leader and a follower. But I come from you might find an article about my beginning of academic career. It's now in SSR, and I posted it somewhere. But when I was growing up, in a small town in Rajasthan, I'm a member of a very large family. I'm the 11th child of my father. I'm the youngest. And so I've seen as a kid what's going on, So my sister becomes 14 or 15. And my mother says, "Dad, try to find a husband. He is the leadership of the mother telling the father, and he has to go find out somebody, right? On the other hand, the father gives the money to the mother every month, saying this is the budget, and the mother has to figure out how much to spend on clothes and how much to spend on vegetables. You see, there is a leader and there's another leader. The different decisions can have a different leader and different follower. And I call that as a mixed leadership game. So you can have an advertising leader. So Devjit can be advertising leader, I could be a follower, but I could be a profit leader and he could be a follower, right? So this is a model of mixed leadership. So I developed the Stackelberg game stuff for mixed leadership games. And so I may not get to there, but there is a paper that we published in Siam Control on mixed leadership games. Exactly what I'm talking about. So that's kind of the title. And then there are two applications. One is a operations management application. One is an advertising application. I may not go through all of them, but the papers exist and the slides do have all that I'm going to talk about, but I may not get to there. My plan is to make this maybe more of a lecture than a seminar. So please ask questions. And if you learn half of what I'm saying, that's better than if I give you the whole thing and you learn nothing. So it's better that you ask questions and we proceed that way. Okay. Okay. So here is my, yeah. Some things I can forward quickly because it's not necessary to. So this is something you already know. So I'm just going to go quickly on this one. So we have a supply chain. It's a very simple supply chain. So we have a supplier, we have a retailer, and in our old supply chain, the supplier basically says wholesale price, and the retailer then gives the order quantity. So you can see that when the supplier says the wholesale price, he's trying to set the wholesale price to maximize his profit. And then the retailer is responding to the wholesale price. And in that response, he's trying to maximize his profit. But one thing you want to know is that the response is a function of wholesale price. So if I give you a wholesale price of $10, you might order 20 items. If I give you a wholesale price of $5, you might order 40 items. So it's a function of the wholesale price, okay? It's important to get this terminology. And this is the self-serving actions. They do not maximize the profit of the entire supply chain. Every marriage people know that a wife's objective function is different, husband's objective function is different, and somehow there are conflicts. So the total profit of the family is not always maximized by maximizing each one's independently. So you have to make those compromises. Those compromises are contracts. Those are the contracts that will coordinate various incentives. Okay, so if you don't coordinate, then there is something inefficiency in the sense that if you were to coordinate, the profit of the supply chain can be $100. But if you don't coordinate, the profit of the wife could be 50 and the profit of the husband could be 45. And $5 is still sitting on the table. So that $5 has to be captured by some kind of a arrangement, some kind of a coordination, okay? And so that is what's called a coordinating contract. The coordinating contract is called, in our field, double marginalization, because the wholesale price is basically the supplier sets up a margin on this cost of production. So the cost of production is $5, you said $2 margin, he will set the wholesale price of $7. So he makes $2 margin. And then the retailer gets it for $7, he puts $3 margin and he sells that to the customer at $10. So there's a margin and there's a margin. And these two margins are then called double marginalization. The double marginalization is nothing but inefficiency in the supply chain. Okay. Maybe a bad word in some sense, because I can give you problems where there's no margin and the two parties are not coordinating. So it's just basically a mathematical concept of nesting optimization, which is much more general, but This is the word that is stuck, and we're going to keep that word. Okay. This is model is a Stackelberg game. So before I go into Stackelberg game, everybody knows about Nash game. Stackelberg games are more complicated, but the Nash games are well known. And there is also a movie called Beautiful Mind. And so we will first define what a Nash game is and show a little bit of a clip from the movie. So in the game of two or more players, a set of decisions made by the players is called Nash equilibrium. If no player can do by changing his decision while the others stay with their decision. Okay, so this is one of the definition. On the other hand, if one person change the decision while the others stay with their decision, and by changing that decision, that person improves his lot, then it's not a Nash equilibrium, because then I can change it and I can improve it. So that's kind of idea of Nash equilibrium. I also want to say more mathematically, if you have a single person, single firm maximizing profit, then that profit is that idea is expressed by one inequality. The one inequality says optimal decision makes bigger profit than any other decision. It's a one inequality, okay? Equilibrium with two people is two inequalities. One person changes, the equilibrium decision is better than any other decision that will be obtained by changing while the others stay. And the second agent, the same thing. It has its own inequality. The equilibrium decision of the second person is better than any other change that second person makes while the first person doesn't change. So when you have two agents, we will not go from 2 to 3 because 1 to 2 is the biggest conceptual change. After 2 and 3, it is just mathematically more complicated, but there's nothing new coming in. Essentially, nothing new is coming in. So we will have two inequalities versus one inequality. So equilibrium is defined by two inequalities. Two people. Okay, so we're gonna. I hope the sound plays here.
Incoming, gentlemen.
Aye.
Nash, you might want to stop shuffling your papers for 5 seconds.
Not buy you gentlemen beer.
Oh, we're not here for beer, my friend.
Oh,
Huh.
anyone else feel she should be moving in slow motion?
Will she want a large wedding, you think? We say swords, gentlemen. Pistols at dawn.
Have you remembered nothing? Recall the lessons of Adam Smith, father of modern economics.
In competition, individual ambition serves the common good.
Exactly.
Every man for himself, gentlemen. And those who strike out are stuck with their friends.
I'm not going to strike out.
You can lead a blonde to water, but you can't make a drink.
I don't think you said that.
All right, nobody move. She's looking overhead. Right, she's looking at Nash.
Oh, God. All right, he may have the upper hand now, but wait until he opens his mouth. Move last time.
That's the history book.
Adam Smith needs revision.
What are you talking about?
We all go for the blonde. We block each other. Not a single one of us is going to get her. So then we go for her friends. But they will all give us the cold shoulder because nobody likes to be second choice. What if no one goes for the blonde? We don't get in each other's way. And we don't insult the other girls. It's the only way we win. That's the only way we all get laid. Adam Smith said, best result comes from everyone in the group doing what's best for himself, right? That's what he said. That's right. Incomplete. Okay. because the best result would come from everyone in the group doing what's best for himself and the group.
Ash, this is some way for you to get the blunt on your own. You can go to hell. Governing dynamics, gentlemen. Governing dynamics. Adam Smith. What's wrong?
Yeah, there we go. Careful, careful.
Thank you.
Okay. So I'm sure all of you have seen the movie, but you never focus on a particular part of the clip where you see the speech here. You see, at least you see how NASA's thinking is developing. He goes from Adam Smith being Adam Smith needing a revision. Then he said Adam Smith is incomplete. And finally he said Adam Smith is wrong. So he goes 3 levels right there. He's talking about the invisible hand where everybody wants to do their own thing. There's a lot of things going on right now, but capitalist economy and the social economy and the politics everywhere. It's all part of big thing here. But anyway, so he goes home and he writes his PhD thesis, which is 26 pages long. And that is where he develops the idea of Nash equilibrium. Once again, the equilibrium is what he's talking about. The equilibrium is where everybody maximizes, but also the group. The group means the equilibrium. That means that there's inequality, but I'm allowed to change only my decision. While I'm doing that, other people cannot change their decision. So that's just kind of in some sense, that is a coordination going on there. But so the group, the equilibrium is not an optimization problem. It is somewhat more complicated than optimization problem. Okay, so the other thing that I have is not important, but the question is whether the Nash's advice forms a Nash equilibrium. Because if you think about it, everybody is going to the brunettes. Only one person can change his mind to go to the blonde, and he's better off according to the criteria here. So it is not a Nash equilibrium. So whatever Nash's advice is here is not a Nash equilibrium, but that is that. So we're going to now go to take the same game, but make it much simpler. First of all, we're going to make it 2 people and 2 ladies, 2 girls, and we will make it a Stackelberg game. So instead of Nash game, we make a Stackelberg game. Try to see what is the difference between Nash and Stackelberg, and you develop that relationship a little bit further. And when I was doing this, I distinctly remember my younger daughter saying, "Dad, brunette and blonde is not politically correct. You know, you prefer blonde and not brunette. It's not politically correct." So I said, "Okay, I will change the blonde to Emily and the brunette to Linda." So this is her contribution to my slides. So we have here 2 people, Tom and Dick, and we have 2 girls, Linda and Emily. Everybody prefers Emily for whatever reason. We're not going to name that. And Linda is the second choice. Okay. Now you can see that there are 2 Nash equilibria here. So Tom chooses Emily, Dick chooses Linda. That's one Nash equilibrium. Tom chooses Linda, Dick chooses Emily. That's another Nash equilibrium. Because if you change your mind, you get nothing according to the criteria, right? So you can change the game. That's a different story. But Nash equilibrium that Nash proposed doesn't tell you how to get there. Economists talk about Teutonment procedures and stuff like that to how to get there. All he talks about is what it is. How to get is another story. We don't also worry about how to get there. But those are the 2 Nash equilibria, and how to get there may depend on other issues like bargaining power and other things that we develop afterwards. Okay, but anyway, so now let's try to. So first of all, here we already got that, and we now go to the next thing to have a Stackelberg equilibrium. Okay, so as you can see, Stackelberg wrote his book in 1934, and that's where he develops the game aspect. You also know that our famous book The tome written by Morgenstern and Paul Neumann was in 1944. There he developed the idea of zero-sum games. It is a big book. But von Neumann is famous for game theory. Stackelberg actually came out before that book, but von Neumann had already written a book in German called Parlor Games in 1928. So he's certainly one of the biggest contributor in game theory, and many other things. Von Neumann was one of the giants of the field. My own professor used to know Morgenstern. George Danzig, I worked as a postdoc, actually knew von Neumann himself. He also tell me stories about von Neumann. Both of those people I have stories from, but maybe we'll talk about that later. We'll continue with the seminar right now. Okay, so here's the same problem formulated as a Stackelberg game. So now Tom is a leader, Dick is a follower. We already talked about that. So now the response function has to be optimized for every decision that Tom makes, right? It's the wholesale price and the order quantity. Now it is the Tom choosing a girl and he's choosing the other. That has to be a function of the girl that Tom chooses. So the function can be written as a table. So here's the first function. I call it a purple. The other one is yellow. The other one is gray. The third one is that one. So there are 4: purple, yellow, blue, and gray. And as you can see, that's a function. Function of Emily is Linda. Function of Linda is Emily. That's the function. Okay. So we have these functions. And remember, the follower doesn't choose the girl. Follower chooses the response function. It's a very big difference. That is the big difference between them. So Dick's 4 possible response functions are purple, yellow, blue. And given Dick's best response function, which is purple, which you can easily find out, it's clear that the Tom's best action is to choose Emily. And so we have an equilibrium called Stackelberg equilibrium, where Tom chooses Emily, Dick chooses Linda. So because Tom is a leader, he gets a first mover advantage. So he gets the best girl in this case, and the Dick basically goes the other. Now you look what's happening. If Tom deviates, right, if Tom chooses from Emily to Linda, he loses. Given that he chooses Linda, then the best response from Dick in purple, given that the Dick still has a purple response function because he doesn't change the response function. And if this changes his response to yellow, remember the change of the Dick is not changing the girl, but changing the response function. This is given that Tom has already chosen Emily. So what is going on here is the obvious difference is that a Nash involves a simultaneous decision. They are deciding the girls simultaneously, okay? Whereas in our game here, the decision is sequential. One person decides and then the other one decides responding to the decision. So we have a first mover advantage. And the subtle difference is that when we check the Nash equilibrium, the Dick's deviation is going from one girl to another because we have to test the inequality. Whereas checking for the Stackelberg equilibrium, the change of the Dick is changing the response function from purple to yellow, green, gray, whatever. So that is a big difference. There is also another difference, but is very subtle. I will come to that in slide 24, but it is not something that most people know. And it's something that I will mention to it when we come to slide 24. So we finally found out that somehow or the other, some differences in a very simple problem between Nash and Stackelberg. Now we go from one period to 2 periods, or one period to many periods. Turns out that when you go from one period to multiple periods, there becomes a lot of different kind of decisions that come into play, and that depend on what information people have as you go along. I'm going to give you 2. One is called open loop, one is called feedback. But there are others. But if there's a paper in SIAM control that I wrote, and you can find out many other different kinds of equilibrium decision multi-period, but these are 2 is enough for us. So one is called the open loop, and we're only going to go 2 periods. One more thing, even though I developed some of the theory later for n periods, But once again, in mathematics again, going from 1 to 2 period is the most difficult. 2 to 3 is just more complication, but nothing conceptually new coming in from 2 to 3. But 1 to 2 is complicated. So it's conceptually completely different than just 1 period. So let's look at it. We have 2 period games now, and we go back to our supply chain, wholesale prices. So we'll have a wholesale price in period 1, wholesale price in period 2, order quantity in period 1, order quantity in period 2, right? Think about if the supplier announces the wholesale price in period 1 and 2 at the beginning of the game. Let's call it W1, W2. So supplier announces W1, W2. What do the retailers do? The retailers' quantity is Q1 and Q2, first period order quantity, the second period order quantity. Q1 will be a function of W1, W2, and a Q2 will be a function of W1, W2. So you can see that even first period quantity is a function of W2, and the second period quantity is a function of also period function 1. Okay, so it is more like that. And so what is going on here is mathematically it is a single period game. Everything is decided all at once. In physical terms, it's dynamic, but mathematically it is just a single period game. In the sense that W1, W2 can be a vector, call it a W, and a Q1, Q2 be a vector, call it a Q. So Q is a function of a vector called W, and you solve the problem for the two decisions. So because it's a single period mathematically, the first mover advantage continues. Okay. But the drawback is that the second period decisions don't take into account what happens in the first period. Suppose first period random demand is stochastic, right? So you order some quantities, and the demand then materializes at the end of the period 1, but you are not allowed to change. So the demand has changed. If the demand is higher, you order something and your inventory will be depleted, you might want to increase the order in the second period. Or if the demand is totally low and you are stuck with much more inventory, you might want to reduce the second period quantity that you had already decided. So you see, you're not taking into account the world being realized at the end of the period 1. And that is a drawback, it's a serious drawback. In other words, the decision in the second period is not time consistent. That, in the other words, that I could change my decision in the second period after knowing what the demand was, or after knowing the resolution of the uncertainty, whatever the uncertainty there was. I could revise my decision. And if revising the decision, the leader benefits, the leader would say to the retailer, by the way, I told you the wholesale price was W2, but I changed my mind. I'm going to call you I'm going to decide W2 prime, which is different than W2, because that is in my interest. Go ahead. Yeah? Distribution is known by everybody, but the realization is not. No, but okay. First period has to be expected value. Yes, if you have a stochastic problem, absolutely correct. You maximize the expected probability, that's all you can do. No, you can improve your decision because the first period is gone. You don't care. The order quantity is already decided in the first period. Yeah.
And suppose I ordered less than the demand.
Whatever, yes.
Then are you assuming that the demand is lost or it is forward in the next period? If the demand is lost, then in the second period also, if we assume the same.
No, it's a 2-period problem right now. It's a 2-period problem. Game ends in 2 periods. So whatever is left over, you can assume it to be salvaged or discarded. The game ends in 2 periods. It's only a 2-period problem right now. Yeah, in the second period, after I realize the demand, I will decide to change my wholesale price. What time dependence? What is the time dependence? What do you mean by that? What if my profit improves by changing the decision? What are you going to do?
There is no dependence between time 1 and time 2. If you are assuming independence,
I don't know. I don't understand what you understand. There's no assumptions here. Absolutely no assumption.
time 2.
It's a very simple problem. Don't change the problem. If you have a distribution of demand, the demand will be known at the end of the period 1, and demand will be known, so you can satisfy the demand. There will be leftover inventory, which you can carry the next period if you want, right? And next period, you have another demand that we don't know yet. But whatever dependence is, you can use that dependence, the demand 1, to find out. So you have you can use a different distribution at the end of the period 1. But anyway, let's talk about this later, okay? Because what I'm trying to say is that if you do an open loop game, there has to be a commitment. Any kind of a decision require a commitment. Economics people call it a commitment. So what they're saying is that we have decided to agree on this and we cannot change it anymore. The problem is that games of full commitment it requires some agreement, and agreement requires, if you go to the economics literature, they say the court will enforce the agreement. So you sign a contract, right? And the court will enforce the contract, but the problem is court has a finite penalty on many of the civil cases. They're not going to hang you for changing your decision, right? So my question now is that suppose the court's maximum penalty is $1 million, and by changing the decision, I gain $1.2 million, then I can change the decision, right? I pay the penalty. But no one has solved that problem. If you look at the entire economics literature, they call it an infinite penalty. Infinite penalty is just hanging, right? You are not going to allow to hang people just because you change your wholesale price. So basically the problem remains in some way, okay? So now we're going to go to the feedback. We'll talk about later if you want. The feedback solution, what happens, supplier announces only the first period wholesale price, but when he decides that, he makes some anticipation, okay? And in period 2, he then announces the second period wholesale price after observing the inventory or after observing whatever uncertainty is realized. By the way, this is a full information game. We are not talking about mechanism design where you have a different information, I have a different information. This is not an asymmetric information game. Everybody knows everything, okay? The only thing is randomness. Nobody knows what the resolution will be until it's resolved. Okay, so in period 2, the supplier announces the second period wholesale price, the retailer response, period-wise. Both take into account the state observed in the second period, which is the inventory or the demand, whatever, and the solution is time consistent in the sense, it's kind of like a dynamic programming, right? Everything is decided from backward, and then when you follow the decision, everything is time consistent. Yes, Debjit? It doesn't matter.
It could be dependent.
It can be dependent, but then what happens is you know the demand in the first period, you realize, then you get the marginal distribution. But the marginal distribution now is the distribution for the demand. But everybody knows that. And so according to that distribution, the demand will be realized in the second period. If it's independent, you don't have to worry about that. But it doesn't really make any difference. So the solution is time consistent, and the first mover advantage only is period wise. So what I'm going to propose is that I'm going to propose that the coordinating contracts that we're going to develop for a 2-period problem or an n-period problem will be a feedback. And since I will be able to coordinate the supply chain, the first mover advantage is not important anymore because I will maximize the profit of the entire supply chain. So suppose I squeeze the money that is left on the table, let's say that was $5 in my example, I will be able to squeeze all $5. And then that $5 can be shared between the two people. So everybody will get what they would otherwise get in the decentralized decision making, which was total $95. One get 50, one get 45. But that $5 can be now split. And that split we're not going to talk about, but that split can be depending on the bargaining power. One can get $2, one can get $3, one can get 0, one can get 5. But that's another story, okay? So what I'm trying to say is that we will be able to coordinate the contract. We'll get what is called the first best solution, which means the decision made by the two parties when the two parties were one company. We'll give that example later. Okay, so this is where the first example I'm talking about. I'm going to now develop a feedback contract for two-period problem in this problem, okay? And we'll go through the but before I will first define the problem, then I will go back to defining that dynamic Stackelberg equilibrium, and then use that equilibrium to find the contract. Okay, so those are the part of the thing. So this paper is now dated. It's 2015, as I said, about 10 years ago. And what I'm going to do is instead of demand being stochastic, I'm going to make the problem stochastic in a different way. So I need a stochastic problem, but demand being stochastic will give you a solution which is not in closed form. Okay, so it is somewhat, it was not available, but we could do that now. But because it's not closed form, it is maybe I publish this paper where everything is in closed form. So what I'm going to do now is make the cost of production stochastic. And there is a paper by Wright in 1936 that said that if you double the production of the aircraft frames, you can reduce the cost of production by 20%. This is the empirical paper in 1936. This is not the Wright brothers, even though there's a plane there. It's not Kitty Hawk. It's not a biplane, but it is another Wright. Different Wright than Wright brothers. And there is a reason for learning curve effect. It's called production cost learning, and it declines through learning. It's because of labor efficiency, better use of equipment. There's a lot of things going on how you learn, and I'm not going to talk much about it because there's a huge amount of literature and economics on this. And so all I need to know is that there's learning taking place. Okay. So the only thing I need to know is that learning is dynamic and stochastic. We all also know that the cost will fall based on the cumulative production, because more you produce, more you learn. Okay, so you will be able to model that. Okay, but empirically, the rate at which the cost decline sometimes may not be deterministic, especially when the semiconductor manufacturing production was taking place in the time I was writing the paper. You did not know how the costs are going to fall because everything was new. The processes were new, technology was new. So all I want to know is that the cost is stochastic. So now let's look at that paper here. So if you put the centralized problem, then it's a problem of manufacturer, and the learning creates an interdependency between production cost and demand, product cost and the production quantity. And I'm going to assume the demand to be price dependent. And so the optimal production quantity, you could observe that in a benchmark case, you might want to have a lower price initially in the period 1, because the lower price will allow you to sell more. When you sell more, you will learn more, and you have a lower cost in the second period production. So that dependence is there, and you can make use of that dependence. So you may not be myopically, the price may be, different price may be optimal in the first period, but dynamically, you might want to reduce the price lower than what is myopically optimal, okay? So the problem would be price and production. You have to set price and you have to decide how much you want to produce. And in the second period, the learning takes place, you sell the market. Let's look at this problem in a decentralized setting. A decentralized setting, manufacturer decides on wholesale price and production quantity. And then the learning takes place. And the retailer decides on retail price and ordering quantity, which is going to be a function of these guys. Okay, so these will be decision in a decentralized setting, and we're going to find out how to achieve coordination when learning curve is present. So I have a two-period model set up, and there are two sections in the paper. I will start on assumptions. I'll give you those, and after that, there's an option that nobody can carry inventory from one period to the next. So whatever inventory there is in the first period has to be discarded. Then there is a second section where the inventory has to be used in the second period. Then the state of the system in the system would be cost, because the cost is changing, and inventory, because the inventory is also part of the system. So in the first period, there's only one state of the system, which is cost. The second period, the two states. Both are solved in the paper. This is just slightly more notation. So I'm not going to present that. I'm going to present this as first part. It is in the paper in the second part. Yes. But
I think are the decisions for the two period taken upfront, or are they decided?
No, we're going to do the feedback. So you'll see how we're going to do it. It's going to be coming, okay? Because open loop has a serious problem, because nobody takes into account the state of the world that is happening. So you're leaving an information that is available to you, but you're not making use of it. You understand? Because you already decided everything. So not insisting on a decision that you already made and not taking into account a decision that is coming to you is a sheer folly, right? There's no point talking about, oh, well, my expected cost will not be minimized or maximized, or profit will not be maximized. You have to, if there's the information that's available to you, if you don't take into account, obviously you're going to lose something. So we're going to take into account. Okay, so our model goes like this. There is a paper by some Nobel laureates on learning, which says that the first period is called the infant stage, where you learn. The second period is the mature stage, where you don't learn. It's a two-period game. So we're going to have a demand. The demand is going to be AI minus B times PI. We're going to assume B to be constant only for simplicity. You can make it BI also if you want. And WI is the wholesale period in production I, and the demand will be linear. C1 is the production cost in period 1. C2 is the random cost of production in period 2. And small c2 will be the realized production cost in period 2. That will be your realization. Okay. The random variable, which is a learning rate, is called lambda. It has a distribution. Okay, so this is our stochastic distribution that we want to talk about. The production variables are QI for the retailer's order quantity, and a big QI, which is the manufacturer's production quantity. And II will be the inventory. I suppressed it because this is section 2 of the paper, which we are not going to talk about. But it's a slide covers both. So, okay. So the game proceeds like this. In period 1, everybody knows the cost of production. It's known. Okay. I separate the inventory. You're going to assume 0 for the time being. Okay. Start with a 0 inventory. So the manufacturer will decide on W1 and the capital Q1. He said, okay, this is my wholesale price. This is my production quantity. Given those, the retailer will decide on retail price and the order quantity. Once that's decided, the infant stage happens. Learning takes place. When learning takes place, C2 is realized as C2, small c2. Everybody knows what small c2 is. And given that information, the manufacturer will now decide on W2 and Q2, having that information. And after that decision is taken by the manufacturer, the retailer will decide on P2 and Q2. And then the game ends, right? So this is our game that we're going to develop. And we will see that if you do a decentralized setting like this, then it will not maximize the profit of the entire supply chain. So there will be a double marginalization. And then we'll develop a coordinating contract and show that under the coordinating contract, that double marginalization disappears. So we are coordinated the supply chain in 2 periods. So that is the program for this paper. So once again, linear demand is DI times AI minus BPI. The state equation of the system, every time you have a dynamic program, there's something called a state. So the state here is basically the cost of production. So this is a stochastic equation. C2, which is the random variable, is C1 minus the lambda, which is the random variable, times the Q1, which is the production quantity you produce. Okay, more Q1, more learning. But lambda is not known. Lambda will be realized. Lambda is a learning rate which has a distribution between 0 and gamma. That means the minimum value means no learning is taking place. And maximum gamma means the maximum learning takes place. Learning can be anywhere in between, right? Now it turns out that in general setting, you need the distribution. But because this problem is somewhat simple, when we do the formula, we'll find out that all you need is mu and sigma. You don't need all the other information given the simple nature of the problem. But in general, you will need the whole distribution. So we will only need the mu and the sigma, and we'll see the formula in our coordinating contract. We only need mu and sigma. Back orders are not allowed. In our first model, nobody has an inventory carryover. Manufacturer retailers are forward-looking, which means whatever, and the Stackelberg game. We will do the Stackelberg game. We're going to assume these only to avoid, because these are innocuous assumptions. They only make the formula a little bit more complicated. So for example, if you take the first order condition, your optimal is, let's say, U star, but you are not allowed U star negative, then what do? You say max U star comma 0. That's what you do. So you put the price at 0. So we don't want this max and min things going on. So we're going to assume these guys, which are nothing to do with the problem, but just to do with the presentation. Now, if you have a single agent, which means the whole company is one company, the two manufacturer and the retailer are together, then it's just a straightforward 2-period dynamic programming problem. You go from backward, you solve it, and when you solve it, it is basically doing this. This is the second period. The profit is given by price time what you're going to sell. You're going to sell minimum of these two quantities. The demand is D2 times P2, whatever the P2 will be. Q2 is the amount you produce. So depending on which is larger, you sell the minimum of those. And the cost of yours is C2 times Q2, because C2 is the random variable. And the period 1 is this one. You take the expected value, and then you maximize this sort P1 and Q1. It's called a nested optimization. That is what's going on, okay? Optimal policies, solving the dynamic programming problem, you can find out that the P1 star is this price, and P2 star is this price. Because remember now, P2 star is a function of small c2, because we are doing backward. We already know what c2 will be. We decide the price for every small c2. So whenever the c2 is realized, I'll be able to make that decision. Okay, so this is the function of c2, and this is the quantity, and here's the profit. The C1 is given fixed, so I just put it just if it is possible to think about this problem where C1 itself is a random variable, and it's realized only after you make a decision. Then you will have to put C1 there. Okay, so there's a profit, so you can see everything is closed form formula. And now we have to go to the next level of how to solve this problem in a decentralized setting. And before that, I will give you the equilibrium definition of Stackelberg game. Okay, so this is, and then we'll go back to the coordination. Okay, so in a dynamic setting, profit of the manufacturer will depend on C1, W1, Q1, W2, P2, P1, P2, everything. And then you will see what it is. The profit of the manufacturer is wholesale price times the order quantity. That's the revenue is going to get from the retailer, minus the cost of production times the big Q1 because he's producing big Q1, the C1 times that is the cost, and W2 Q2 minus big C2 Q2, and there's expected value. Retailer's cost is also a function of all these guys, but the retailer is getting P1 times the demand, which is the amount he sells, minus the cost he pays to the manufacturer, plus P2 times this minus that. Okay, so these are it's a different formula as a profit than in the, yeah.
But there will be chance of holding costs.
Well, you can make the holding cost if you carry the inventory, but this is that I'm not carrying any inventory. You can go to the second period, then you can have a holding cost if you want. You will find out that in this case, the production quantity and the order quantity will be exactly the same. Yeah. Huh? Yes, it will be the same in this case. Yeah, you will get the formula. So, but it is again, I think the main purpose here is to not question the model because it's a simple model. Main problem is to see how the Stackelberg equilibrium is implemented. And this will hold, for example, even the lambda distribution it could be a distribution. So you can make the problem more complicated. Again, ideas can be, so this is not, you're right. And there's a state equation. So this comes for my definition of a Stackelberg equilibrium. And I will develop that definition for n periods, not just for 2. And most of it is notation. You need a notation to write down things. There's not much mathematics involved here other than the proof later, which I'm not going to present. Okay. But right now, in order to define the equilibrium, I need to develop a notation. So let's go through this notation. Okay. So in a feedback Stackelberg equilibrium, the leader determines her strategy. So X, this is the state equation. The state equation could be inventory, could be cost, could be whatever it is. It could be n-dimensional. Okay. So in period I plus 1, the state is xi plus some function of the decision that people will make, the state, the decision u is the decision of the manufacturer, v is the decision of the retailer, the random variable, and the period itself. So you can see that if you begin with the problem at some period t, which is t, and your initial state at time t is y, then from y you can develop this state equation. Okay, so this is the stochastic state equation. And the leader strategy will be a feedback, so that means it will observe the state at any given time x and observe the time itself, and the function will be u of x comma t. And it will be, the follower will react to this guy, so the follower will know the x as well. Follower will also know t, but it will also know that decision, so that decision will come there. So follower will make that decision. So this is the sequential definition of that game now. We can write this as u of x1. You can even want to make it x sub 1 if you want to, but it's okay either way. U of x1, x2, xn is the decision that he makes. I call that as u. And the v is this vector, v x1, u x1, v x2, x2, so this is v. And let now u and v denote the spaces. Now, remember, u can be bigger than or equal to 0. You could be smaller than or equal to m, depending on the warehouse. So there might be constraints. So we will put all those constraints into these spaces. So let u and v denote the spaces of these strategies, feasible stages of these strategies, whatever they are. They can be complicated or simple, but it doesn't really matter for this part. Then let's take any u in this space, any feasible u. And let's take any feasible v in that. Given u and v, I can solve this problem. When I solve this problem, starting with xty, then this is the initial condition starting with a t. Remember, in dynamic programming, when you start from 0 to n, you start with a t because it's time consistent, so it doesn't matter. You have to start in general setting. So initial value ty, the state x at time I given u and a v will be solved by this equation. So the solution of that equation will be that state. And the feedback decision will be function of that state at each point of t. Okay. So now we can see the leader's definition will be function. This is the profit function. It'll depend on at any given time I starting from t to n, because t is the beginning. At any period I, it will depend on the x of that period I, which is already decided by solving that equation. It will depend on a u, which is the decision you make, which is the feedback decision, which is taking into account that x. V is going to take the feedback, and the decision of the other guy, and so on. So we have, and the salvage value of the inventory, if you have this. So this is your decision given that feasible. Same thing for the follower. So what I'm trying to do is give you the notation for the profit of the two agents given any decision u and v which are feasible. Then you define the Stackelberg equilibrium like this. A pair of strategy u star in u and a v star in v is called a feedback Stackelberg if this one is bigger than that one for any u in u, for any y in Rn, which is the n-dimensional state, and any period from t1 to n. You can see what's going on here. I'm changing u. The leader is changing u, but the other guy stays with the decision, equilibrium decision. But the equilibrium decision will, when I change u star to u, this decision will be v star dot u. This is important to know. So that's true. Now look at the follower. The follower will change v for any v, but this guy will stay at u star. So when you change to v, you can see this is still a u star there. So these are the two inequalities that define the Stackelberg equilibrium. They're almost similar to the Nash. The only difference is what you're changing. Instead of changing your decision, oh, sorry. How do I go back? Here. So instead of changing, that guy is changing the response function. So if you make this v similar to u, sorry, what is going on here? Sorry. If you change that u, this v similar to u, it will become a Nash equilibrium. So the difference between Nash and a Stackelberg is basically the space, which is different. The space of deviation is different. And this is slide 24. So let me tell you just briefly what I mean by this. When Stackelberg developed the idea, he actually defined a solution which is actually more than an equilibrium, in the sense that in his decision, in the Stackelberg decision, u star can be replaced by any u in the second inequality. So it will be for any u and any v. You can write that. That simply is too strong. It's not an equilibrium, and it cannot be generalized. So the Stackelberg solution, sometimes I call it a solution, not equilibrium, because it's stronger than equilibrium. But it just happens for a single period. But you cannot generalize Stackelberg solution to a Stackelberg solution in a multi-period setting. In multi-period setting, all you can do is an equilibrium. That's all you can do. So that is the distinction that we will never be able to get the Stackelberg. There's no solution to that. That just doesn't happen. So that's all we can do. So we have a definition of equilibrium. And now what happens is we solve the problem backward, just like we do dynamic programming, and we can develop a table. So when we solve the backward, we start with a C2 and we solve the second period problem first. When you solve the second period problem first, it's just a straightforward problem. And what you get is a wholesale price, you get the production quantity. It's a single period problem. Second period is a single period problem, you just do all of that. And then you solve the first period problem and you get all of that. This is not complicated. Now you want to implement this decision, right? And implement is in forward time. So what do? You solve this problem. When I said in a feedback, you have to anticipate. When you decide something, you have to anticipate what's happening in the future. That is what is anticipation. So what you do here is wholesale price. You already know C1, so you have this formula. You see only mu and sigma there. So you will announce this wholesale price. When you announce this wholesale price, the production quantity will be pronounced by this guy. And then order quantity, which is a function of C1, W1, and Q1, is this formula. So he will decide W1, you put the W1 in this formula, and you will say, this is my production quantity. You put that W in this formula, you say, this is my price. So you see you're developing the formula which already took into advantage of the second period. That's how the anticipation came into the play. And then once you make this decision, the capital C2 is realized as small c2, and everybody observes the C2. You go back to the table, you look at the C2, you put the table, you find W2. Again, the table, you find these two. So this is how you solve the decentralized problem. So we have a feedback Stackelberg solution of a decentralized problem, which is the Stackelberg equilibrium. How much I'm doing time-wise? Okay, so let's go to the equilibrium, the coordination contract. But let me say something before I go. Remember, I'm putting W1, which is the wholesale price here. It is the dollar amount that I'm putting. I'm not putting a function. What I'm trying to say is the following. You see here? This is not a function. It is what he will announce given x and t. Because if I put that in a function, then I have a function of a function. And that is a calculus of variation problem. It is not a problem that we can solve easily, although you can get another kind of idea there, but it is a more complicated problem. And so we don't have any, because then the whole history becomes important, and it is not a feedback Stackelberg anymore. It's not feedback anymore. Feedback is taking into account. Okay, go ahead. Question?
Yeah, non-zero sum.
This is a non-zero sum game. Yeah.
In some non-zero sum simultaneous games, there are some nice structural results if the number of periods is infinite.
Yeah.
We don't have nice results if the number of periods is large, but it is still finite. So I'm curious if you have, even though you have done this for finite time horizon, whether how these results will kind of maybe stabilize in the finite.
The second problem, infinite horizon. The infinite horizon problem. Okay, the reason of simplicity in infinite horizon, first of all, this guy disappears. There's no salvage value at infinity, so that disappears. And the other thing is that solution U will become stationary. It's only a function of x, not of t, because the stationarity comes from the fact that anytime t, the future looks the same. But if it's a finite horizon period n, then when you go to the n, then the remaining period is changing. So in the beginning of time, you have n period remaining. Second period, you have n-1 period remaining. Third period, n-2 period remaining. But if you are at infinity, then there are infinitely period remaining no matter where you are. And so that means that the dependence on time disappears and the problem simplifies in some way. So there are a lot of benefits of that. But the cost, of course, is that no one lives to infinity. It can only be, infinite horizon problem can only be justified as a simplification of the finite horizon problem. And if that simplification gives you a good enough solution for a large horizon problem, then you're okay. Okay, so it has to be, but it has to have some convergences and stuff like that, so that you approximate the large horizon problem by infinite horizon problem. Okay. So the The next part is the contract. So in our field, we have developed something called a revenue sharing contract. We have developed a buyback contract. By the way, in the earlier part of this seminar, I had to develop the entire one without any equation. So I had examples given example of a full coordinate graphs and everything, but that was because it was a named lecture, and the whole school it was invited, and it is not a good idea to have equations when you have people coming in from everywhere. Okay, so and in our field also, we know that the buyback contract and revenue sharing contract are equivalent in some way. So the revenue sharing contract means that the supplier says that I will share revenue with you. Remember, in that profit sharing, because profit sharing is trivial, because then the supply chain profit is being manifest to begin with. It's a revenue sharing, not the profit sharing. The other one is a buyback. So the idea in a news vendor problem, which is really the most important problem in the supply chain coordination, the idea is that people tend to under the price that whatever you charge is not the price which is optimal for the supply chain. And so what happens is that the retailer doesn't order enough. And the retailer doesn't order enough because he doesn't want to get stuck with whatever is not sold. So when he doesn't order enough, then manufacturer also loses some profit because he could have ordered more. So the manufacturer wants the retailer to order a little bit more so that what he order is what the order will be in the benchmarks, single monopoly supply chain, decentralized supply chain. So he says, okay, I will buy back what you don't sell at a certain price. So whatever price you set at buyback will allow me to order more. If I give you more buyback, I will order more. If I give you even more buyback, I'll order more. So there is one buyback price where I will make sure that your order is exactly what the order of the centralized optimum is. So that's the whole idea of buyback. Same as revenue sharing. So they are equivalent. Okay, so I'm going to now develop the revenue sharing contract, which is this. The manufacturer proposes a revenue sharing contract with a set of contingent wholesale price and revenue sharing rates. So I'm going to give you a wholesale price and the share of the revenue, and the wholesale price and the share of the revenue, where the share of revenue is between 0 and 1. And this is the retailer's forming. This is the form of revenue sharing contract in 2 periods. In a single period, it will be just this contract. Just remove it with this contract. W and phi on a 1 period problem. Remember, the second period problem is a single period problem. So now I give you a contract. So let's not worry about this because this is the new objective function under revenue sharing, which is easy to because you see the phi one is the revenue share. So this is the total revenue, this is the share of the revenue, this is the cost, this is the share of the revenue, this is the cost, the expected value. So the problem under revenue sharing contract is this objective function. So here's the proposition. For any phi 1, phi 2, if this is the wholesale price in period 1 and this is the wholesale price in period 2, then this is a coordinating contract. You notice that this formula is the same formula that you see in the news vendor problem in a single period. It is just the phi times the cost of production. But you see this formula is more complicated. So the period 1 is more complicated. It takes into account mu and sigma in this case. And this is now the coordinating contract between the 2 parties. And it's a flexible contract, just like we had in the single period, in the sense that any phi will do. And which phi finally gets implemented depends on the bargaining power. If the supplier is Walmart or Amazon, they can squeeze all the power from the retailer. So the phi will be 0 and whatever, okay? And in the other cases, maybe the retailer is powerful, then the retailer gets all the profit. Supply is more powerful, then supply gets all the profit. And if the power is shared, then there's a Nash bargaining solution or whatever, which will give you the fight. But we are not interested in that. We are just interested in saying that there is a coordinating contract. I will only spend a little bit of time on the mixed equilibrium to just very quickly to see what's going on. This is a paper in Siam Control in 2019. And the mixed leadership comes because there is a thing called cooperative advertising. So what is a cooperative advertising? Let me give you the slide here. So the cooperative advertising, the participation rate where the supplier says or the manufacturer says, I'll give you a certain percentage of your advertising expense. Because what happens is the retailer does not advertise enough for the benefit of the manufacturer. And because it doesn't advertise enough, there's not enough demand. But if you advertise more, the demand will increase and the manufacturer will benefit. So it is in the interest of the manufacturer to say, I'll give you a certain percentage of advertising. So that is called cooperative advertising, and then the amount of contracts that are involved are billions of dollars. So there's a lot of cooperative advertising going on. There are empirical papers, for example, the amount of estimated in 2007 were already $25 billion. I don't know what it is now. And there are marketing papers that tell you, what is the percentage of cooperative advertising. But there is no paper in marketing that tells you what is the optimal percentage. But for that, you need the model like what I'm doing, right? So I don't have an empirical model here, but I have a model that will tell you what the optimal percentage would be. So you see IBM is 50% of advertising costs, Nature Bounty 50%, Apple 75%. But what should be the participation rate is one of the things that I can handle here. There are some papers here on cooperative advertising. And then that's the paper I talked to you about. This is the first time that people have looked at the Stackelberg problem in multi-period. So it's a 1979 paper, long time ago. And we have our own papers are here. This is my paper. And this is my paper. That is the one I'm presenting right now, is this one. So we develop sufficiency conditional optimality, but these are a little bit more mathematical papers. So here is a kind of a Nash-Stackelberg game, because what happens in this setting is that this is the leader and this is the follower. So what happens is the manufacturer announces the which is the participant rate, and the retailers announces his participation. So in my model, what is going on is the retailer can also give some support to the manufacturer's advertising. So each support are advertised together, and then given the two supports, the amount of advertising that these two people will be also announced. So you can see the two decisions, both are leaders in allowing the participant rate, and both are followers in determining the total amount of advertising. So that's the kind of model we solve here. And then there is a stochastic differential equation with the Brownian motion here that is based on the SETI model, which is 1983. There's a Wikipedia page for that as well. There's a paper in recently OR with the title Generalized SETI Model. So this is one I developed in 83. And so there's an objective function, and we developed the game. And anyway, in the end, we solve this problem, and we give you some graphs and stuff. So I'm just not going to talk too much about it. So I'm going to conclude here. Okay, so I gave you some difference between Nash and Stackelberg game, gave you two types of Stackelberg equilibria, then provided a definition of what a feedback Stackelberg equilibrium is. I gave a paper on dynamic pricing and production and develop a supply chain coordinating contract. I give you a mixed leadership game of cooperative advertising, not much, but a little bit. And then there are some papers that are available on this field. So here is a, thank you very much. Meaning of what?
learning rate.
Oh, the learning rate is in the sense that more you produce, more you learn. But the rate of learning depends on technology or whatever. And in our model, it's stochastic. It can be, I just make it a simple model. The thing is that I need to have a model which is stochastic. Otherwise, I'm not going to do anything. Coordination is required, that there's something that is changing at the end of the period one, so I can take that into account. So that's exists. Now, in Newswender problem is the demand which is stochastic. But then the demand is not dependent on price. In my model, the demand is deterministic, but depends on price. But the cost is stochastic. In the Newswender problem, the cost is deterministic, but the demand is stochastic, but doesn't depend on price. So those are the two different models. And there is a paper on the Newswender problem that, okay, there's a little bit of history here. This problem that I gave you in 2015 started maybe another 10 years earlier. And by the time we got this, there was a paper in EJOR, which are two Korean people wrote a paper using the Newswender problem, but they don't have the idea of Stackelberg equilibrium in the paper, but they do develop a contract, and they also make some mistakes. So the mistakes are not so critical, but we provide those. So there is a Newswender where, but it's not a closed form solution. Like I gave you the closed form solution, it's not. So it is possible to have a 2-period contract, which is not closed form, and use this idea here. So, but again, I tell you, this is as simple a model as I can get, so that I have a closed form formula. But it's rich enough in everything. It has a random component, it has dynamics, it has everything. So, and it uses the definition that we have. So that's all I can say right now. I'm not going to defend the model because it's so simple. It's more like an example, right, of a theory. Any other? Yeah.
This reminds me of a work by Anand et al. In management science. I'm not sure whether you're aware of that. There is a paper by them which talks about a 2-period model. And instead of learning rate.
You mean the Ravi Pindi's paper?
Sorry?
Ravi Pindi? No.
It's about strategic inventory.
Yeah. So I know that paper.
So from period 1, the retailer can actually buy more than what he needs, so as to carry over the inventory to the next period, using which he can bargain for a lower price in the next period.
I know, but they don't coordinate.
But there, I think towards the end, they talk about 2-part contract which can coordinate this supply chain.
I don't remember that, but in any case, they don't have a Stackelberg equilibrium definition at all. So I don't know what they mean by coordinating. Without the definition, you don't know what it means.
I think what it means is probably you can get the
Yeah.
first best.
Yeah, but whether it is an equilibrium has to be shown, because if it's not equilibrium, then it is a forced. So here's what I mean by this. If I was a supplier, I can tell you order that much. If not, I have a gun in front of me. And what are you going to do? You're going to order that. But that's not the decision you're going to make on your own, because for that, I have to tell you that it's an equilibrium. Without equilibrium, I can, by fiat. Now, I agree with you. The paper is not wrong. It's just that it is not complete.
No, I agree. I think what they are saying is probably 2-part contract can improve, but probably not get the best.
So we had an extension of this where manufacturer can carry inventory. Right now, the retailer does not carry inventory. The manufacturer carry inventory. We had that, but they wanted to remove everything to make it simple. But you're right. There's a strategic inventory which gives you the bargaining power in the second period, and you can show all of that. But that paper hasn't been written yet. Yeah, it's there somewhere in the notes, but it is now the world has moved to AI, and maybe it's not any more important to publish that paper. Maybe, I don't know. But you're right. It is.
Right now, you have talked about contract. Does the 2-part tariff also
Yeah.
Yeah.
So there is a paper that we are currently working on. It's called 5 Steps to Supply Chain Coordination. The first part is a single period. The second part is a 2-period. And we developed an idea where all the supply chain coordination paper in single period can be derived by one formula. Yeah. So in multi-period is not yet complete. The single period is complete. The multi-period that is still the paper has not been finished yet. But yes, the same thing. It's basically 5 steps for any problem, and it has a generalizing contract terms, like contract terms of 5.1, 5.2, 5.3, whatever they are. And you need enough number of terms to be able to equalize the quantities to the centralized profit, and then they become algebraic equation to solve. That's what the entire supply chain literature. So yeah, let me give you what I'm talking about. So the world of supply chain coordination did the following. They developed benchmark profit. They developed the decentralized solution. And then they equated the benchmark for the decentralization and found out these terms of the contract and solved that problem. And then it ended. And we are saying there's a step missing. The step that's missing is this. When you have a supply chain, under the revenue sharing contract or any other contract, the objective function changes. Right? It's a different objective function than the objective function that we had before, right? Somewhere here. It's different. So what I need to show is that under that contract, if I solve this objective function, then I get a Stackelberg equilibrium. That is, you can think about 2 ways. One is that whatever they did automatically gives you this. The other one is to show it. So in our 5 steps coordination, we show that everything that is done in supply chain coordination literature actually satisfies this. But they show it, but you can show it that they satisfy. So that's part that is, in my opinion, it has to be shown. But if you say it is automatic, then you have to show that it automatically satisfies. But nobody has talked about it in the literature. So without that, it's not an equilibrium, because there's new objective function. So that's what I mean by that. But good that you pointed out that paper. Any other thing? Oh, I have some, if there's a time, I think there's well, let me talk about it. My PhD coordinator gave me a slide show for, not a slide, but a few slides about our PhD program. So I'm going to talk without this, because otherwise we have to upload this. I have it on my USB. So UTD PhD program that I started when I went there, because without that, there's an article I wrote about how to grow an OM department. It's in POM, first paper in 2005 issue, the January issue of the POM. So one of the things you have to do is you develop a PhD program. And of course, now we are one of the big PhD programs in the country. And so I just want to say that especially now, there is a starting this year, I think most universities are going to have some issues about getting PhD students, because our PhD students come from, where do they come from? They come from China, they come from India, they come from Korea, they come from Iran, and very few come from the United States. And so people are now trying to figure out, how to attract PhD students. So I have a little sales pitch about PhD students. So, but you guys are already PhD students. This would be a seminar for MBA students to say, hey, rather than do a clerical job, to have a car and a servant in your home, you can do a PhD and have a good life being your own boss. I would not trade my life with any company work, but but that's that. So that was kind of we are now paying. Our students are getting almost $200,000 salary for 9 months. So 12 months, they usually give 2 months salary for first 5 years. So that's called 2/9. So if you take 2/9 and $200,000, you're getting something like $240,000 a year. And in Texas, when I went to Texas, then the house was about 1 year salary of my 1 year salary was the house I bought. Gross salary without paying taxes. Now, my colleague Anyan bought a house maybe 1.5 times his salary. Now it's 2 times his salary. So 240 plus 240, 480,000. You can buy a 4-bedroom house in Texas, 3-bedroom, 4-bedroom in Texas. So I don't know any country in the world that can give you a house, freestanding house, for 2 years of your gross salary. India will be 30 years of your gross salary to buy a house, more or less. And every country, even the United States, in California, it will be a lot more. But Texas, for some reason, we can say that we are, in terms of house, we can probably beat any country in the world. So, and then we give you, I think, $10,000 or $15,000 travel conferences kind of money. Only this year, the dean has said, if you need more than 15, don't come to me. But all these years that I've been there, people wanted to go to another conference after the $15,000 got depleted. The dean will always give me some more, as long as it's a conference which is reputable. But this year, there's a letter saying, because every university has a little bit of a problem right now because some of the Indians are not coming and they were paying fees. I don't know about your time. When I went there, the only students that I saw from India were PhD students, because those are the only one who got money. And anybody who came to, other than this, did not exist, because nobody in India had the money to send them overseas. And even if they had the money, there was an exchange rate regulations. I remember what happened to me when I went there. The dollar changed from 5 to 7.5 rupees within 6 months of, when I started doing it was 5, then when I left, 7.5, and all of a sudden we had to spend more money, 7.5 rupees to get $1 instead of 5 rupees to get $1. That's 50% extra cost, right? So that's the story. So now you go to any of the campuses in the United States, there's a lot, all Indians everywhere, undergraduate program, graduate program, and they're paying fees, huge amount of fees to the universities, and they're going to lose some of that because of our president's decisions. Hopefully it will not last too long, but you never know. So anyway, pass the word and come to Hanoi if you want to. Hanoi is a great city. Have you ever been to Hanoi? Anybody? I've been there, but it's Halong Bay is one of the best bay which you can visit. If you like good food, Hanoi is a good food. And the cost is not so high, by the way. I'm doing 8 days by car and a driver after my conference, and they are telling me that it'll cost me about $950 or something. It's not very expensive for 8-9 days. So that's pretty cheap. So anything else? Okay, well, thank you very much for
So thank you, Professor Sethi, for this fascinating talk. I'm sure we all enjoyed the conversations. And Professor Sethi was telling me that he still visits his office every day a week. In fact, Saturday, Sundays, he also spends there. So I'm sure in the coming years, we'll see more of your influential works. And yeah, wish you all the best. Wish you a very long, healthy, prosperous life.
He didn't tell you that I'm in town only like 7 months of a year. 5 months I'm somewhere else. But those 7 months I do go to the office on Saturday and Sunday.
Yeah. No, it's very, very inspiring. I think if we can take even some learnings from your life, I think that is very inspirational. Thank you so much for visiting us. Thank you. Thank you so much. And Prahlad, we need to come over. Sachin, please come over. Himanshu, we need to come over. Yeah. Let's give a token of gratitude to Professor Sethi. Yeah. Please come over. Please come. This, you can come, all of it's.
Oh, thank you.
This is the jolly that you saw the